So we're going to talk about ways to prove triangles congruent. Oops. And I'm going to qualify that with the word some, because we're not going to get them all done. Now, this comes out of lesson 4-2. This chapter is so large with information that we actually end up having 2 quizzes in this chapter and a test. Okay? That's how big this is. And I think, chapter 1 we had a test, right? And then we had a quiz and a test, and a quiz and a test. This one is so major with so much stuff that we actually break it down into 2 quizzes and a test. So we spent a long time on this chapter, chapter 4. Okay, and interestingly enough, nobody asked me about the question on the homework from last night. That was, I think it was 22, and where you were supposed to draw triangles and based on the description, and then would you guess that your classmates' triangles would look just like yours, or would they not? And you got some yeses and some nos. Well, today we're going to talk about why you would get yeses. They're actually postulates. So that's, see, I tell you, we keep kind of previewing something in homework, and then we talk about it coming up. All right, so when 2 triangles are congruent, the 6 parts, we talked about that yesterday, of one triangle, so the 6 parts include 3 sides and 3 angles. Bless you back there, are congruent to the 6 corresponding parts of the other triangle. Corresponding meaning they are in the same position on the 2 different shapes, okay? So think about what a pain it would be to have to get 6 pieces of information to match up in order to say, yes, these 2 triangles are congruent. So guess what? I'm going to make it easy on you. Instead of having to get 6 pieces of information correct, you got 3. You can get 3 pieces of information congruent, then you can conclude that you have triangles that are congruent. But they have to be the right 3 pieces of information. So that's the fun part. You only have to work half as hard. It takes only 3 pairs of congruent corresponding parts. To prove triangles are congruent. Okay, so we just saved ourselves a ton of time. All right, way 1, and guess what? All 3 of these have names. So we just need to use the name when we use them in a proof. First one. Postulate 12 is called SSS postulate. Okay. So remember what we're trying to do. We're trying to prove 2 triangles are congruent, and we're trying to have 3 sets of corresponding parts congruent to each other. What do you think SSS stands for? Side, side, side. And that's exactly right. And that was the 4th one that you guys had to do last night in your homework, was try to draw the triangle with the specifically named lengths of each side. And they gave you a big hint, which was probably the only way to do it, is to actually cut out strips that were that long, lay it out, and then trace. Because it was to try to get exactly them to fit, angle-wise would have been challenging. But that's the first one. Okay, and it says, if 3 sides of one triangle are congruent to 3 sides of another triangle, then the two triangles are congruent. Okay? So SSS stands for side, side, side. Okay? So a little diagram of this situation. So this is triangle ABC, triangle DEF. And I'm told that AB is 3, AC is 4, BC is 5. I'm told that DE is 3, DF is 4, and EF is 5. Because side AB is the same as side DE, and side AC is the same as side DF, and side BC is the same as side EF, I can conclude that triangle ABC, oops, that didn't work. Try that again. ABC is equal to triangle, and you have to get the letters in the right orientation. AB corresponds to DE, BC corresponds to EF. So we can get triangle ABC is congruent to triangle DEF. Drake P. No, because we're talking about a triangle. We're talking about an object. That's where the congruence comes in. And by the way, there's no way to write the measure of triangle ABC. Okay, we can only do that with measures of angles and measures of sides. Okay? All right, so now I have a vocab word that's going to come up in the next one. And this is the word included. Now, included means a lot of different things depending on the situation, but in geometry class, included indicates an angle between two adjacent sides. So adjacent sides means they have an endpoint in common. Or a side between two adjacent angles. So it can either be used with sides or it can be used with angles. So here's two triangles. Let me just highlight in color. If we have two adjacent sides, this would be the included angle. It's between them. In fact, it's the angle that those two sides form. That's what makes it included. If we have two angles, and you would draw them out, this side was chosen once, this side was chosen once, this side was chosen twice. This becomes the included side between those two angles. So it was the side that they shared in common. Okay? I'm going to write common side. That idea of included is important because it's part of the next two postulates that we have that are two more ways to prove that triangles are congruent. So the next guy, postulate 13, he's called the SAS Postulate. What do you think that's going to stand for?
Side, angle, side.
Side, angle, side. Now notice that the angle is between the two sides, so that word included. Okay? We are going to have a very stern conversation about not altering the order of those letters for fear of you creating something that I like to refer to as the naughty postulate. I will just leave that for that moment up to your imagination to understand what it is, but we will discuss in detail later. Okay? So this says if two sides, I've actually, people use the naughty postulate on a proof, and I'm like, it doesn't exist. It is my way of saying, you rearrange the letters, you spell a naughty word. Don't do it. It doesn't work. Okay? If two sides, oops, and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the triangles are congruent. Okay. So if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the two triangles are congruent. So we've got two triangles, A, B, C, D, E, F. I'm going to tell you that segment AB and segment DE are congruent. And I can tell because they have the same marks on them. I can tell you that segment AC is congruent to segment DF. Okay, and again, they both have the double marks to them. And I can tell you that angle A is congruent to angle D. Because angle A is included between the segments AB and AC, and angle D is included between segment DE and segment DF, then I can use this side angle side postulate, and I would be able to conclude that triangle ABC would be congruent to triangle DEF. Okay? All right, last one. This is going to be postulate 14, which is ASA. Oh, that reminds me, postulate. Let's go back to the one from the page before, and let's add that this stands for side angle side. That's the SAS. Okay. So what do you think ASA stands for?
Angle, side, angle.
Angle, side, angle. So that says you've got an angle, and there's a side between that angle and the next angle. So it's the common side of the two angles. So if two angles and the included side of one triangle are congruent to two angles and the included side of another triangle, then the triangles are congruent. And again, in parentheses, this is angle, side, angle. Okay. So in this diagram, triangle ABC, triangle DEF, and we've got that angle A is congruent to angle D, angle B is congruent to angle E, and the side between those two angles, segment AB and segment DE, are congruent to each other. we can conclude that triangle ABC is congruent to triangle DEF. Now, the bad part is they don't always put things in a order. They sometimes reorient the shapes, or let me give you a second example. So we've got triangle MON. It has segment the length of MN is, length of MO is 4. We've got a right angle, and I know that one of the other angles is 55. Okay, and then I've got triangle KEY, where the length of KE is 4 and that angle at E is 55, and we have a right angle. Because I have two right angles, because I have two angles that measure 55, because I have the side between them that both has the same measure, I can conclude that triangle MON is congruent to triangle KEY.